Welcome to CSC 201, 10.4, trees, examples and basic properties. So we have a definition of a tree here. A graph is said to be circuit-free if and only if it has no circuits. And a graph is called a tree if and only if it is circuit-free and connected. A trivial tree is a graph that's just a single vertex, and a graph is called a forest if and only if it is circuit-free and not connected. So we have some examples of trees here. This one, it is connected and it has no circuits. This is a trivial tree. This is a tree, it is connected, it has no circuits. Same with this one. Some non-trees. Okay, A is not a tree because there is a circuit right in the middle here. Okay. Same with B, there's a circuit right here. C has a circuit. D is not connected. So D is a forest. It is circuit free, but it's not connected. So this is a forest. And what are trees used for? We've seen possibility trees used for counting. So for example, we did this earlier in chapter 9. How many ways can this tournament be played? We have to count the branches. So we've got 1, 2, 3, 4, 5 branches up top, and this is symmetric, so there are 10 ways to play this tournament. Another use of a tree is a decision tree. So for example, during orientation week, a college administers a mathematics placement exam to all entering students. The exam consists of 2 parts, and placement recommendations are made by following this decision tree. So if we read this tree from left to right, we can decide what course should be recommended. In particular, let's look at a student who scored a 9 on part 1. So we follow this first branch. And then they scored a 7 on part 2, which is greater than 6. So we follow this branch. So we recommend they take Math 110. For number 5, for each of the trees below, count the number of vertices and the number of edges. I'm going to ask you to just pause your video and take a second and do this yourself. And then when you're done, hit play and see if you got them correct. So part A, if I want to count the vertices, we've got 1, 2, 3, 4, 5 vertices up the main branch. Then 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 vertices. And then I want to count the edges. Same tree, count the edges instead of the vertices. So again, going up the main branch, I have 1, 2, 3, 4 edges. Then 5, 6, 7, 8, 9. 10, 11, 12, 13, 14, 15, 16, 17, 18, 19 edges. For B, we have 1 vertex and 0 edges. For C, vertices there are 4 and edges are 3. And then D, vertices we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 vertices. And then to count the edges, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, so just from these 4 examples, a strong conjecture would be that the number of edges is always 1 less than the number of vertices in a tree, right? If you're given a tree, edges always seems to be 1 smaller than the number of vertices, and that turns out to be true. So that leads us to a theorem that if n is a positive integer, then any tree with n vertices, no matter what its shape, has n minus 1 edges. And the converse is also true, though we have to add in the word connected. Any connected graph with n vertices and n minus 1 edges must be a tree. And it follows that if n is a positive integer, any graph with n vertices and fewer than n minus 1 edges is not connected. So if a graph G has 10 vertices and 12 edges, is it a tree? Nope. A tree would have 9 edges. All right, let's see if we can give an example of a graph with 5 vertices and 4 edges that is not a tree. So this sounds like it should be impossible because if it has n vertices and n minus 1 edges, it's a tree, but that's only if the graph is connected. So if this has 5 vertices and 4 edges and it's not a tree, it must not be connected. So I'm going to try to draw this picture. Let's see, I have 1, 2, 3 vertices and 3 edges. I need 2 more vertices and 1 more edge, so I can just draw like that. So that has 5 vertices, 4 edges, but it's not a tree because it's not connected. Okay, so one more definition. I think one more. We're going to let T be a tree. If T has at least 2 vertices, then a vertex of degree 1 in T is called a leaf or a terminal vertex. And a vertex that has degree greater than 1 is called an internal vertex or a branch vertex. And the single unique vertex in a trivial tree is called a leaf or a terminal vertex. Okay, so I just want to list the leaves and the internal vertices or branch vertices. So leaves are just vertices that have degree 1. So that would be this one, this one, this one. Okay, so V naught, then V8, V7, V5, V4, and V2. Those are the leaves, the terminal vertices, they have degree 1. And then the internal or the branch vertices have degree greater than 1. So those are the remaining vertices, V6, V1, and V3.